Hokie dokie. Second example. For this problem, I will work it out a little faster, but nonetheless, it'll be a little different in this version because in this one, they're asking for minimum total cost. If you want to see the example where they ask for max area instead, please visit the other example I've worked out. Also, if you want to see more of a breakdown of this problem, check out the other one. This one, I will cover less of the basics, more of just the process for this. So, when we're looking for minimum total cost, or minimum of anything, we need to find the equation for cost in order to find the minimum of cost. So we talked about in the last video that cost is the north and south prices, so 2 plus 6 times L for the length, plus the sum of the east and west costs, so 4 plus 3 times the width, W. So then simplifying this, we get that the cost is 8L plus 7W. All right, not too shabby. We also need the equation for area. Well, we're always dealing with a rectangular plot, so the area of a rectangle is length times width. And so here we have cost and area in terms of length and width. But in order to find the minimum of cost like we need here, we need cost in one variable. We need it in terms of not L and W, but just, say, W. How do we do that? We need to replace L with something in terms of W. So that's where this extra information about the area being equal to 8,000 comes into play. So we know if area is length times width, and we know that this area is equal to 8,000, well, there we go. We have an equation relating L and W. So that allows us to solve for one variable. We can get L by itself on the left side by dividing by W, since these are multiplied together at the start. So we have 8,000 divided by W is equal to L. So now we have L in terms of W, which allows us to substitute this L in place of this L here. So we can write the cost equation as 8 and not L, but 8,000 over W plus 7W. So this is the cost in terms of one variable. Again, the reason we needed cost in terms of one variable is so that we can find its minimum by taking its derivative and setting it equal to 0 and solving for W. So I'll simplify this just a little bit, multiplying this 8 times the 8,000 to get 64,000. All divided by W plus 7W. All right, the goal, the next step is to find C prime, the derivative of cost. So if we have 64,000 over W, that's like 64,000 over W to the first. So if we were to have rewritten this, let's go ahead and say this equals 64,000 W to the negative 1 plus 7W. So the derivative of this, we bring out the negative 1. We get negative 64,000, and then we subtract 1 from W to the negative 1. So we get W to the negative 2, which I will rewrite that in the denominator as W to the positive 2. And then derivative of 7W is just 7. So we have C prime. Now, anytime we're finding the max or min of something, in this case cost, we find its derivative, and then we don't stop there, but we set it equal to 0. So the goal is to solve this equation for W. We want to get W by itself. So I'll leave 7 on the left side, and I will add this term to the right side. 64,000 over W squared. So there's a little trick I like to do when there's just the variable on the bottom on one side and then just a constant or whatever it may be on the other side. We're going to multiply both sides by W squared and simultaneously divide by 7, essentially swapping spots of these terms. So then all we need to do is take the square root. I don't like that W. Let's do that again. That's fine. Take the square root of this stuff on the right side. We get 64,000 over 7. And take the square root of that. Let's break out Desmos. Square root 64,000 over 7. we get about 95.62. 95.62. Let me double check just to make sure I've done that right. All right, that seems fair. We have our width. And something I mentioned in the last video, the other example for this problem is that the width, whatever we get for the width, should be basically the width or the location for which the area is, it's the width for which the cost is at a minimum. So naturally, it'll be the minimum of the function we are looking for. If they were instead, like in the other problem, asking for max area, it would be the width of the max area. We don't necessarily have to check whether it's a max or a min. It's sort of a waste of time in these problems. So we can assume that this is the location of the minimum cost. In other words, this is the width for which the minimum cost occurs. So if they're looking for the minimum cost and we have the width where that happens, all we do is plug this width into the cost equation. Well, which cost equation? We had 8L plus 7W. We could do that, but then we need to solve for L, which we could do, but it'd be a two-step process. So instead, look what we have here. We have the cost in terms of W. So we can just plug in the W value we just got into this cost to find out what the minimum cost is. So we're plugging in this width into 64,000 over W plus 7W. So in place of W, of course, we are plugging in 95.62, 95.62. Let's see if we can do it in here. 64,000 divided by 94, what did I say? 95.62 plus 7 times 95.62. All right, 1338.7 if we round. 1338.7. We're dealing with dollars. We are dealing with the cost. This is the minimum cost, essentially, for this. So we have about 1338, and we have about 1330 to 1340, okay? Break out the eraser, and we see that A is our answer. Hopefully this makes some sense. If you have any questions, let me know. If you need more of a breakdown, please visit the other example. Surprisingly, this is probably still like 8 minutes. The other one was still 11. It's a long process to explain, but hopefully it makes some sense. It's not too bad once you work through it a couple times.